Welcome to Chapter 2 of ICSE Physics Class 10, where we're going to deal with work, energy, and power. Part A, which is just the definitions and understanding of what is work, energy, and power. So let's start off with work. In general, we already know that any object can experience either a pushing force or it can experience a pulling force. So this object can experience either a pull or a push. Now, generally, if this object is not pivoted or not joint or restrained, this push or pull is going to cause the object to move. So let's assume that this is where the object was and this is its new position due to a force F. So if the distance between this is S, which is displacement, then we have to figure out a mathematical quantity that'll be useful for us to solve various problems in real-world scenarios. And scientists realized that we could call that quantity as work. And that's going to be equal to the force into the displacement. But it's very important that the displacement is in the direction of the force. So what does it mean in the direction of the force? This means that when we apply a force in this direction, it's not necessary that the body is going to also move in this direction. Let's take a look at an example of such a scenario. Over here, we have a ball that's in front of an inclined plane. If we are to apply a force on this ball, then the ball physically cannot move forward in this particular direction, which is the direction of the force. The reason why the ball cannot move in this direction is because it's going to hit the slope or the ramp, and it's going to be pushed up along this ramp. So the ball would move in this sort of a direction. It would actually roll up the inclined plane and land maybe here. So we applied the same force F and we got a displacement of S meters, but the displacement is not in the direction of force. The displacement is in this direction, whereas the force was in this direction. So how do we figure out what is the displacement in the direction of the force? We'd have to drop down a perpendicular and know that this distance now is the displacement in the direction of the force. So we have to find out what the value is. If the angle at which we applied the force and got the displacement is theta, in that case, this particular distance is going to be the original distance that it moved, which is S, times the cosine of theta. Now we've already gone through what cosine is in trigonometry and math, and we will go deeper into why this is over on the Diane Academy channel. So be sure to check that out. Remember, for this particular chapter, there's going to be a lot of numericals, derivations, and explanations given over on the Diane Academy channel. So it's very important that you watch those videos to score well in your exams. So with this knowledge, we can state that the work done is not just force into displacement, but it's the force into the displacement into cosine of theta. Now this cosine of theta can be written as cos theta, and we don't have to write the multiplication sign. So it's just Fs cos theta. Now this is actually the dot product, which is different from the cross product that we've studied in torque. However, what exactly dot product and cross product is outside the scope of your syllabus. So it's just a fun thing to note. Remember that we looked at this by considering exactly how much displacement occurred in the direction of force. But we might as well have considered how much of force was actually in the direction of the original displacement and then considered it. We'd end up with the same conclusion. However, the derivation has been given in Diane Academy. So once we know this, we can actually look at a few special cases where we could actually find out where is the work done equal to 0, negative, positive, and so on. So let's take a look at the first case. What's the possibilities for getting the work done to be equal to 0? That could happen if the force is equal to 0, or the displacement is equal to 0, or cosine of theta is equal to 0. Situations where the force is equal to 0 is pretty self-explanatory, where there is no force occurring on a body. But displacement equal to 0 is a bit more interesting. Imagine we have this wall that's present over here, and you apply a force on the wall. The wall isn't going to move no matter how much force you apply the wall is simply not going to move. That means the displacement is going to be zero. So in that case, no matter how much force you're applying and how much effort you're putting into this task, the work done by physics is going to be zero. The same thing could be said if you had a toddler or any small boy or even a grown man trying to push a big rock that simply will not move. So if the displacement is zero, the work done is going to be zero. Another more interesting example is if the cosine of theta is equal to zero. In that case, theta has to be equal to 90 degrees. For those of you who have forgotten, 90 degrees means a right angle. So this happens in various situations. The best example would be in case of uniform circular motion, which you studied in the previous class. For any object to be rotating, we've studied that the direction of motion is always going to be perpendicular to the radius. Or in other words, it's going to be a tangent to the circle that it's following, the circular path that it's following. So if this is the direction of motion, we also studied that the force that causes this uniform circular motion is always pointed towards the center. That means it goes along the radius in this particular direction. So therefore, the angle formed between the force and the direction of motion is 90 degrees, and therefore the work done is going to be equal to zero. This concept of work done being equal to zero has profound consequences on why uniform circular motion can occur and the speed remains constant. However, to exactly understand this, we'll have to wait for a little bit to go a bit deeper into this particular chapter. Another example for when cosine of theta is equal to zero is when a porter or a coolie is walking with luggage on their head. So imagine this is some luggage. The luggage has some weight in the downward direction, and to make sure that this does not fall down, the porter or the coolie has to apply a force in the upward direction that balances this out. However, there is no motion in the upward direction because the bag remains in the same position. However, the coolie then begins to walk in this direction, and so the luggage also moves along with the coolie in this direction. So in this case, the force that he's applying is in the upward direction, but the motion that's occurring in the bag is in the forward direction. So therefore, the angle is 90 degrees and the coolie is doing no work. But in a real life scenario, the walk cycle would actually have the luggage moving up and down every time he walked. So he would actually be doing work in all of those scenarios. And apart from that, he would also be doing work against the force of friction. So therefore, he actually is doing a lot of work. But in the ideal case, he's doing no work. So now let's take a look at a few examples where the work done is positive or greater than zero. So in this situation, if we take an example of the coolie himself, as he tries to pick up the luggage from the ground and place it onto his head, in that case, he's going to be applying a force in the opposite direction equal to the weight of the luggage, which is going to be mg. Now, most people would think that if he's just applying mg force, the luggage is not going to move up. However, again, this is an approximation where we're assuming that he's already lifting it up and he's moving it with uniform motion. That means the net force might be zero, but the velocity is in the upward direction. The only situation where the upward force has to be greater than the weight is when he starts lifting it and there's an acceleration. But since we don't know how much of acceleration he's doing, we always tend to ignore those areas while calculating things, just to get the understanding of how things actually work. So we're assuming that he's lifting it with absolutely uniform motion, and that's why the force is going to be equal to the weight, and he's going to move that to a distance of h, and therefore the work done is going to be mgh, which is the force times the displacement. The exact same thing could be said if a ball was to fall down simply due to the force of gravity. So the force of gravity acting on the ball is its weight, which is mg, the mass into the acceleration. If it falls a distance of h to the floor, the work done by the force of gravity is again going to be mgh. Similarly, a number of examples can be given where the work done is greater than zero. And even our original example or examples of the block moving or the ball rolling up the hill are all examples of positive work being done by the force F. Lastly, let's take a look at when work done is negative or lesser than 0. For this situation, the cosine of theta has to be lesser than 0, which means negative. Now, to be honest, this occurs when theta is greater than 90 degrees and lesser than 270 degrees. But more than thinking about all of those situations, an easiest situation would be when theta is equal to 180 degrees, because in this case, cos theta is going to be equal to -1 exactly, which makes our equation of work done to be equal to minus force into displacement. So this can occur in many situations and generally occurs when we have a stopping force. For example, when a cricketer catches a ball that goes up and is coming down, it's coming down in this direction. But in order for the cricketer to stop the ball or to catch the ball, he'd have to apply a force in the exact opposite direction. But even as he applies the force in the opposite direction, the ball would still continue to move in the same direction for a little bit of time, which means he does negative work. The same thing occurs in general when a ball is thrown up. The motion is in the upward direction, but the force of gravity is in the downward direction. So in this case, the work done by the force as it's traveling up to a maximum height of h is going to be minus mgh. Hopefully that gave an insight into the different situations of force and work done. There's one last thing that we have to cover, which is what happens in case of a variable force. So in case of a variable force, we use various techniques that you'll be studying in higher classes. But an easy thing to note is that if you have the force or the value of force on the y-axis and you have the displacement on the x-axis, and we see that the force starts off being 0, maybe at this point it starts increasing to a maximum point. And then at this point, the body maybe continues moving, but at a constant speed, which means the force on the body is now 0. So the body starts off with uniform motion over here because displacement is there, it's moving. But then the force starts increasing on the body, or force starts acting on the body, and it continues moving. And then eventually it continues moving at constant velocity again. That means during this section where the force is acting, the body is actually going to be accelerating. However, in a situation like this, we'd simply have to find the area under the curve to find out work done. So hopefully this answers a few other questions for you. For example, if the force is constant, in that case, we simply have the area of this rectangle, which would be the value of force into displacement, which is just F into S. So that makes sense because this is exactly what we got in case of work done, where the force is constant. And it also explains another very important point, that what exactly the displacement is. This is something that students get confused a lot. If a ball is to start moving due to a force, let's say we apply a small force F and the ball starts moving and then the force is removed. Now the ball has some velocity and it continues moving with that velocity forever. So is the displacement considered infinity? Most students get confused the moment they think about this scenario because the force was applied and the ball is moving forever. So the displacement should be infinity and hence the work done should also be infinity. But that doesn't make sense. So it's very simple to realize why that's happening from this graph. The force on the ball is immediately 0. So even though there's displacement, the work done due to that situation is 0. So there's only work done while the force is being applied on the body. So it's during that acceleration phase before it reaches the final velocity that actual work is done, and that's what's calculated. Hopefully that gave an understanding of what exactly work is. We will deal with what the units of work is, the different versions of joule, calorie, and so on in the Dayan Academy video. So be sure to check that out. Till then, we're going to continue with the term energy. In simple terms, energy is the capacity to do work. That means if a body possesses energy, it can technically do work. So energy would actually be the maximum amount of work that the body can do. If work is done on a body, the body gains energy. And if a body does work, then the body will lose energy. That's pretty much all there is to energy. So the units of energy would be the same as work. So all of the formulae would also be the same as work. However, in order to determine what exactly the capacity to do work is, scientists have found other units or certain units that work better for energy than for work done, and certain units that work better for work than energy, although technically the units work out the same. Different types of energy exist, but that will be taken care of in a future chapter. So this is all you need to know about energy. It's a very short part of the chapter. The last thing we need to know is power, and power is the rate of doing work. That means in general, power is equal to work done divided by time. So this means that if something can do more work in the same amount of time, that means it consumes more power. Or if it does the same amount of work in lesser time, then it also consumes more power. So there are a few units of power which we'll also deal with in the Dayan Academy video. And also, since power is work done by time and work done by itself is force into displacement, since we divide the entire thing by time, we can actually separate this out to make it force into, we all know displacement by time is velocity. It's actually force into velocity, which in this case would be the average speed, since it's the total distance by total time. This is just a very small fun derivation, which is used a lot in higher classes of physics. Hopefully that gave a good enough understanding of what exactly work, energy, and power is. And once you know all of the units, derivations, and the relationships between the different types of unit, then you would be completely ready to solve numericals. And we will also have a separate numericals video over on Dayan Academy's channel. So stay tuned and all the best for your exams.